Don't go on yet. It's not even open yet. You're going to do that at the end of the class. Just now, right now, work on paper, circle your answer, because you're going to turn in that paper with all the work on it. And then when I get done teaching all the topics, because there's a few more problems down below, then I'll open it up and you can feed them in.
These ones don't have the
triangle.
They don't have the so for this we go all the way around.
Yeah, you can go anywhere you want for when you're solving equations. I mean, you got to stay in that interval that I said, 0 to 2 pi. Don't give any answers beyond that. But you could twirl anywhere you want. Call me over if you have questions. Can you tell me what problem I got up to in the outline? I think it was I got up to 12.
No, we got 12.
We did do 12?
No, that's the wrong one.
Yeah, we got
7-3.
We didn't do 12.
Oh, we didn't do 12 yet? Okay, so I'll start there. Thanks. You know what, I think for the people that were not here, why don't we stop a minute and if you can function on your own because you were here for the whole thing, go for it. Go ahead. But this is for the people that were not here. I'm going to do a couple of them just to get you flowing again so that those people could maybe more successfully do the problems. Okay, so it's not going to be these, but it'll be like the ones you're doing. Like, for instance, you guys are doing all first degree right now, right? So here's another example. And if you want to take your outline on, we can add to your outline, and at the same time, me give you an additional example. This would be number 12. Because some people are lost because they weren't here. All right, so this was the basic gist of it. You're being asked. Now, this problem asks you, the only thing that's different for you people that were here, the only thing that's different in this problem is that they ask you for a general formula that will generate any and all answers if you were to continue rolling around the circle. But let's say that we're doing it like the ones you're doing on the quiz. You know that everything I told you to solve so far, before we got to number 12, has been find the answers between 0 and 2 pi, not inclusive of 2 pi. So why don't we solve this as though we were doing it that way, and then we'll go for the general formula. So for the people that weren't here, almost all the problems that we solved the other day said find any answers you can between 0 and 2 pi. I will say to the people that weren't here, the difference between this section and the last one is that you may spin into any quadrant you want, no restrictions. The only restriction you have is if I say, hey, don't give me any more than those answers. Okay, so even when you're given the general formula as they've asked you for in number 12, you still start like this. You're still going to start like this, just like you did the other day. So this is what I'm looking at here. I bet you a lot of you, maybe not every single one of you, but the good majority of you know what the reference angle is for a number like this. What is it? Well, it has to be 45, right? Because aren't we getting square roots of 3 and stuff like that and 1/2 whenever we're talking 30 or 60? So this has to be reference angle. You know, the reference angle is the most important thing in these problems. If you already know what the reference angle is, you could essentially cut out a lot of the drawing. What's really important is the reference angle. There's no way that the sign could be this if this wasn't the case. Okay, we've been practicing speaking in pi language. What do you have to divide pi by to get 45? 4. Okay, so we're fourths. Because knowing the reference angle on the denominator will help you get the real answers. Okay, so let's see. Now we want to think about where is the sign, and you can write the theta if you want. Where is sine of theta positive? Because that is what you're looking at here. You're looking at a positive value. So the sine being like the y-coordinate, it really is y over r. Where is the sine value positive? Which of the quadrants should you be in with your drawing, even if you don't draw the whole thing? You should be in 1 and what else? And 2. 1 and 2, right? You know really when I'm doing these problems, the only thing I'm interested in is the twirling arm, the hypotenuse. I don't care if you put the rest of the numbers on the triangle, because some of you, when you start to realize that that's really all you're using is the hypotenuse, you'll understand that the only reason that I put those numbers on the legs for you is that you will successfully figure out what the reference angle is, but you already know what the reference angle is. So why do I have to tease you into it? I really don't have to. Okay, so you said I can be in quadrant 1, or you can be in quadrant, this one? No? This one, over here. Okay, so those are the quadrants you can be in. In this quadrant, I don't care whether you're using all students take calculus, because if you are using that saying, you still get that sine is positive there and there. Or if you're just thinking of the sine as a y, and the y is positive there and there. So look, if you already know that the reference angle is pi over 4, why bother with the rest of the triangle? This is all that matters anyway. Where is this arm? Right here, because this is the reference angle. That's all that is. We've been struggling here in this class and with all my classes to get the difference between theta and reference angle. What is the real theta when you're in quadrant 1? Same. It's always the same as the reference angle. That's the only quadrant where that's true. I'll keep saying that. But once you move into quad 2, 3, or 4, then this is no longer the same. Okay, so I gave you like a little crutch, how to figure out where the rotating arm is. In other words, the hypotenuse. Now, if you want to, go ahead and complete the triangle. It's not going to do anything for you. The crutch that I gave you is for you to think of 1 pi and 2 pi. We're not going to come over here, so I don't need to worry about this. In terms of that denominator, 1 pi is the same thing as 4/4. 2 pi, if you did have to come over here, which we don't, is the same thing as 8/4. Okay, it's a matter of just matching the number when you want a 1, doubling it when you want a 2. Because in that way, it's very easy to figure out where you've rotated to. How many fourths are you at right here if you never made it all the way to 4/4? You stopped 1/4 before you got there. 3/4. Okay, you should be getting really good at doing fractional answers, fractional pi answers. So yesterday, or not whatever yesterday, Tuesday, if you were solving the problems according to these directions, you would come in here and you would go like this. I don't really care if you put the set symbols or not. You would put your first answer and then your second answer, and that would have been it. That's what we did last time we saw each other. Now, on number 12, the directions have slightly changed, so let me tell you how to get the general form of an answer. The general form of an answer means that instead of you stopping between 0 and 2 pi, you continue spinning to your heart's content and give an equation that exemplifies the places that you need to stop. If you're trying to give an answer for this particular problem, only place you're allowed to stop are where those arms are, right? So can't you always land right on the same spot when you're spinning around a circle just by going a full revolution, 2 pi? So that's going to be part of my equation. I'm going to say that one of my answers is that, okay, this is called the general form of the solution equation. And let me see how they're trying to drill it out of you. Okay, so you'll talk about where you stop. Let's do the one in quadrant 1. We're going to give a general equation for all the solutions that could be had in quadrant 1 if you just kept spinning around over and over and over again. As long as you stop on that arm in quadrant 1, you're talking about a solution. So we're going to go add any kind of multiple of 2 pi, and you're right back where you started. 2 pi, 4 pi, 6 pi. Anything that makes you land there will give you a reference angle of pi over 4, and therefore your sine will be square root of 2 over 2. Now let's give an equation for the stuff happening in quad 2. So this is the equation that represents all the solutions in quad 1. This is an equation that represents all the solutions in quad 2. 3/4 plus any multiple, that's what k means, any multiple of 2 pi. That'll make you land right back on 3/4 pi. Okay, those are called the general solutions. So on your outline, in that first blank, put pi over 4 plus 2 pi k. Those are the ones in the first quadrant. In the second blank, put 3/4 pi plus 2 pi k. Okay, now go back and see if maybe with the people around you, you can continue on those problems. See if you can do a few more of them. Call me over, please, if you're getting stuck. I don't want to do the next one in the outline, not yet, because I don't want to freak the people out that weren't here. Because that was the harder ones, the ones with the 2 in front of it. What?
So I remember you saying like you can't go past it. So like.
You're thinking the 2 sections that came before that.
No. Okay, so would it be?
You're allowed to spin whatever you want.
So it would be pi over 6 and 11 pi over 6.
Well, let's just see. 1/2. You decided that this one here, the 1/2, good. Therefore, that was square root of 3. Therefore, that had to be 60, which is, where's your little reference angle? Pi over 6? But I don't think that's true. Because if this is square root of 3 and this piece right here is 1/2, isn't the square root of 3 always the long leg? Okay, there's never a 30. You just said that that's pi over 6. That's 30 degrees. The 30-degree angle is never across from the long leg. It's the 60-degree angle that's across from it.
Okay. Okay. So then it would be pi over 3 and then 5 pi over 6. 5 pi over 3. Right?
Well, what do you want? You want the cosine to be what? We're positive?
Mm-hmm.
So, yeah, you could be over here, you could be over here. So, let's see. Pi over 3, yes.
Mm-hmm.
And then if you went here, yep, you got it.
Yes.
Second answer I gave you. 3 pi over 4.
We put that here, though. There's 3 answers.
There's 3 answers.
No, there's not. Oh, you got to give answers off of it. Okay, so list the first 6 solutions that are greater than or equal to 0. Okay, I'll help you do that. Just plug into the equations I just created for you. And the k can be, I'll do that with you, but the k is allowed to be anything from 0 and bigger. It's like 0, 1. I'll do it with you. So maybe we'll get 3 off of the one equation and we'll get the other 3 off of the other equation, which is kind of it's a hassle, but.
So for number 3, because the x is positive, does that mean that it has to be in these 2 quadrants?
Yeah, because cosine's x, and x is positive over here. So yeah, you got it in the right quadrant. Okay, now where does the cosine go? But I would reduce this. This should have been 1/2.
Oh, I put 1 over 4.
All right.
That's the whole problem.
And if you want to, you could just, when you're doing these problems, you could use the entire fraction if it says cosine for the x leg. And the entire, instead of like how I split it up when I go x over r, I mean, you're still going to recognize it. Because even if you do split it up like that, okay, let's say you're doing it exactly like I do it. Isn't this double that?
Yes.
Okay, that has to be the short leg then. Therefore, what's this piece?
Long.
Good. All right, now make the biggest decision of the problem. What's that angle across from the long leg? Just go like this. What's always across from the long leg? Is this
16.
good? Which is the same thing as pi over 3. Pi over 3. There you go. And then that one.
And then this is, that one is pi over 3, and then this one would be 6.
Good, good, good.
And then 6 pi
Excellent. Good job.
Negative 5 pi over 3.
No, not negative. No, this is 1 pi over 3, 2 pi over 3, 3
Oh,
pi.
I was thinking about that.
Yeah, no, you're spinning in a positive way. You're thinking of the section before this where you have to spin. Yeah, but you don't have to. You can spin in any direction you want. Anybody want to ask anything? Let me squeeze in there. Yeah. For every problem that I did in the notes the other day, when it was first degree, I got the word by itself. So yes, that would be the first step. Make a drawing. Go to where cosine is, what do you have there, a -1? Go to where cosine is -1. You cannot draw a triangle whenever the problem involves zeros and ones. That's the time you can't draw a triangle. You can make a drawing, they just won't be triangles. It'll be you rotating around the circle and identifying where the cosine's negative. Yeah, that's when you can't draw the triangle. Anytime there's zeros and ones in it. All right, so right there is where the cosine, because cosine's the x. All right, so right there, what's that location called? Pi over 2, 3 pi over 2, what's it called? Because that's what you're trying to ultimately find, the theta, how far you've rotated. Right, and that, where you're standing, what's that called? It's pi. There's your answer. If the problem has zeros and ones in it, you're going to have almost no work. They're not going to be like these, because you'll have no, you'll have no reference angle. That's why they're not that much work. Hey, people, when you're going to do numbers 4 and 5, you understand that your picture should not have, because wasn't step 1 get the trig word by itself? We got to get that in our head. Step 2. Think about what quad you're allowed to be in. But when the problem involves zeros and ones, as numbers 4 and 5 do, there's no quad to be in. You're going to be right on an axis. Therefore, your picture won't be a triangle. It'll just be you rotating around the circle, right? And in those cases, you only have one answer. Like for number 4, when you got cosine, wasn't it cosine equal to -1? Cosine's the x value. And there's only one place on the circle where the x value is -1. You should have one and only one answer, no triangle in your picture. These are the easy ones. They'll be 1/4 of the work that these are. Almost no work. Just rotate to the place where the cosine, what is the place where the cosine's -1? Pi. That's it. End of story. Done with the problem, hardly anything to do. All right, I'm going to move on. What?
So yesterday when we did the tangent, we still drew a triangle.
Yeah, we always draw a triangle unless the problem has to do with zeros and ones.
Also, if it's negative, you would still -1, you would still draw the triangle.
Yeah, but tan's a different thing, because tan, the reason that I'm talking about all zeros and ones. The only reason that tan can ever come out -1 is because you're at 45 degrees. Because isn't it true that when you're at 45 degrees, this leg's square root of 2 over 2, and this one's square root of 2? So when you go y over x, that's how you get a -1 where the tan. So for that, you'll be able to draw a triangle.
Here, since it's -1, we would basically just rotate from here to here.
Let's see. So yeah, positive y, negative. Yeah, that quadrant's good. Okay, and then where else you got it? Quad 4, 3. No, that won't work. Because if you want it to be -1, either one leg or the other has to be negative, not both. And where you're at right here, this leg is negative. You're in negative y territory, which is what that leg represents, and you're in negative x territory. That would not give you I don't know where the problem just went. It would not give you a negative. You're talking about this one?
Mm-hmm.
No, that one there's no triangle for. That's the one we were just talking about.
That's what I'm saying. So you would rotate from here to here.
But wait, I'm going crazy. Weren't we just talking about tan equal to -1?
Yeah, I was going based off of this one.
Okay, yeah. Okay, to help for that one. All right, so tan equal to 1 is the only one that you could get a 1, and that you'll be able to draw a triangle for. But all these other things, when cosine or sine has to do with 0 or 1, there's no triangle. There's no triangle whatsoever. You're just trying to rotate to the place where cosine is -1. That means you're just on the circle, and you're trying to tell me what axis you're landing on. Because you're right on an axis. Those are called quadrantal angles.
I got a question.
What?
Okay, so, but this one, this would be the short layer, right?
No, square root of 3 is always the long way. Because square root of 3 is bigger than 1/2. Square root of 3 is bigger than 1.
Okay, even with the negative.
Even you don't look at the negatives. It's just the actual value of the number without considering the negatives. Is the short way. Okay.
Gotcha. Thank you.
Okay, let's move on. All right, so I'm going to have to hit you with another hard one. Now, let's finish number 12. Did you see for number 12 that there were 3 spots you had to fill in? The first blank spot you were given the answers that you got in quad 1, which was pi over 4 plus 2 pi k. And then for the second one, you were given the answers for quad 3, which is 3/4 pi plus 2 pi k. And then there was still yet another spot where they told you, the direction said something like, give 6 answers. Well, you have equations that generate infinite answers. Use them. It said, I think, give the 6 smallest ones. So maybe the 3 smallest from the first one and the 3 smallest from the other one. Let's try that. Now, you can mess around with it. I don't have that kind of time left in my life to sit here and do 16 answers, but I'm going to generally tell you how to do it, okay? So let's use the smaller equation, because I know that's going to give me small answers. And you know what k is allowed to be? Maybe you can write this to the side. It can be 0, 1, 2. So why don't we come to the side? So we go k is equal to 0, 1, 2, blah, blah, blah. On and on. Okay, I'm going to start always with the smallest value because that'll give you the smallest answer. So here I go getting my answers. I'm going to do my work over here. Okay, I'm going to use this equation. So theta is equal to pi over 4 plus 2 pi. I'm allowed to plug in for k a 0, a 1, a 2. So I'm going to put a 0. Pretty easy. That'll knock out this whole 2 pi deal and give me just pi over 4. There, I already used one of the equations to generate my first of 6 answers. Okay, then I'm going to go, again, I'm going to stick with this, small. This is a smaller solutions because the front number is smaller than that. So then it's going to go 2 pi times 1. Now I'm moving to 1. I let k be 0. Now I'm letting k be 1. You might want to use your calculator for this. Or if you can handle it, then just do it on paper. Like, for instance, when we're talking force, 2 is the same thing as 8 force, which is equal to 9 force. If you are not into doing that by hand, here it is in the calculator. Okay, careful though, when you enter it in the calculator, don't get too anxious here. All I want you to put in is 1/4 without the pi. You're just trying to get it to help you with the fractions. So just put in 1/4 plus 2. You don't need to put the pi on there, you can just tack it on at the end. And you'll see that when you put that in, you're going to get 9/4. I'll demonstrate for the people that don't know how to do it. Here we go. Let me minimize this. Blah, blah, blah. Okay. Okay, so what did I have? 1/4 pi, but I don't put the pi in. I just go 1 divided by 4, get my calculator to add 2 to it. And this way I don't have to get common denominators and all that. But just hit math and then enter twice. And it'll get the common denominator and add it and reduce it. Okay, so that's 9/4, and that's what I had on my paper. but you got to put the pi back on there. All right, and then if you want, so this is my first answer, this is my second answer, here's my third answer, and so on. This time I'll let the k value go to 2. You can put it in the calculator again if you want to. If you want to get the calculator to help you with 1/4 plus 4. But this is the same thing as 16 over 4 plus 1/4 is 17/4. Anyway, in that manner, you're going to get 6 answers. Now, you could jump to this other equation now and begin getting the 3 smallest answers. Just at the end, make sure you're giving the 6 smallest one, 6 smallest values. So you'll have to compare the 3 that you're getting here to possibly what you could have gotten by going and getting a 4th answer on that smaller one. So I'm going to let you finish that. I just wanted to demonstrate how to use those never-ending equation generators, solution generators. Okay, that's what that's called, a solution generator. It gives you all the solution. Okay, let's move on to number 13. I got to hit you up with this multiple angle thing again. So let's go ahead and do that. I'm going to demonstrate. That was the hardest one that I did. The hardest one I did is when you have either a 2 theta or a 3 theta or something like that in front, because there's lots of extra things. Not lots, enough for it to be annoying. So here we go. I'm going to demonstrate another one of those. This will start off just like number, where else did we do this? Yeah, 11. Did we do the same one? No. Different by a sign? Okay, so it's just like number 11, the one that I'm doing right now, only that one said negative square root of 3 over 2. This one says positive square root of 3 over 2. But it's a good chance for me to demonstrate how to generate an infinite formula as well as going over multiple angle. Okay, so this one starts like this. Sine of 2 theta is equal to 3 pi square root of 3 over 2. Sine of 2 theta is equal to square root of 3 over 2. Okay, here we go. Okay, it starts off, you got to always start off, even if the problem says, give me formulas that generate infinite answers, start off as though you were doing it like the problems I did on the first 2 pages. Okay, so you're always going to start off assuming that you are looking for the answers in the first revolution from 0 to 2 pi. You don't actually give 2 pi as an answer because 0 is the same thing as 2 pi. You don't need to call it both. Okay, so remember that 2, it does 2 different things. We're going to use it at the end, but we also use it at the beginning. Because see, this is called the domain, that you're allowed to get answers over this entire domain. Theta is like the x in the problems. When you're solving a trig equation, the theta represents the x. So that's called the domain, but this doubles the domain. So you're going to come over here, and you're going to double this domain. That means instead of you only being able to give the answers between 0 and 2 pi, you will now be able to give the answers between 0 and 4 pi. Okay, so you're doubling your domain, and you can give the answers anywhere between 2 times 0 is 0, 2 times 2 pi is 4 pi. Okay, that's your new restriction right there. And it's not like a restriction, it's that you're going to stop twirling after 4 pi. And from this, we're also going to give our general answers. All right, here we go. All right, so let's see. So I was telling you that when you solve these, you can solve them as though it's just sine of theta. Just to get you started, sine of theta is equal to square root of 3 over 2. Okay, then think about these things. Okay, this is a review for the people that weren't here. Okay, first thing you do is you want to do a drawing right now. So as you do the drawing, you can't draw it unless you know where to draw it. So you have to temporarily stop and think, where is the sign positive? Who cares if you put the theta? I just want to know where I should go and do my drawing. So sine You can think of it as the y coordinate, and the definition is y over r, so it has to be the y. So where is the y positive like that? Quad 1, 2, 3, 4, or all of them? 1 and 2. We're going to make our picture in 1 and 2. Our rotating arm in those quadrants. So I'm going to have a rotating arm here. You can draw a full triangle if you want. You can put the numbers in there if you want to. And by the way, when you put these numbers here, you can put that whole thing, square root of 3 over 2, on your y if you want, or you can split it. You can split it up according to the definition, where you make this the y and this the r. That's how I've been doing it. Okay, definition for sine is y over r. But just by doing this right here, don't I already know what the reference angle is? Because the reference angle is never about anything more than the leg that goes like this. So if I already have a number there, isn't it true that, what is the angle that's always across from the square root of 3, 60 or 30? So I already know everything I need to know. Why should I bother continuing representing the legs or labeling them? So this is 60, same thing as pi over 3. But please make sure you are clear on the fact that this is nothing more than the reference angle. I'm hoping I can really drive that in you by this chapter. That won't be such a mistake in quadrant 1, but you will make a mistake in quadrant 2 if you don't understand that. You can get away with it in quadrant 1 because this hypotenuse, which is actually the real answer, is always the same as the reference angle. But once you get here, you have to understand the difference. Okay, again, for those people who are learning to count in fractions, this landmark right here is called 1 pi, or 3/3. We stopped. If we're rotating, if we started rotating like this and continued rotating until we got here and stopped right there, that means we never made it to 3/3. We stopped 1/3 before we got there, therefore this is 2 pi over 3. Okay? Okay, now do you remember that 2 theta affecting our problem, that it also had another function, and that you use it right now? You bring it into the problem. Besides doubling the domain, we're going to use it when we go to work with the answers. So we'll work with these 2 answers, but aren't I allowed to continue spinning? So I could really give some more answers than this. I mean, these are the answers between 0 and 2 pi. But if someone says, hey, you're allowed to keep giving different names for the arms that you're on by spinning to that arm an additional time, because they're saying, hey, spin until you run out of room, 4 pi. I could spin around like this and give another name to this angle right here. If I was to go like this, spin full circle, land right on it. That's why the first thing you got to do is establish where the original angles are, and then if you want to land on them again, because you're being allowed to in the problem. So you can get 2 answers right here. They're semi-answers. These are not finished. So let's see, what is this? 1 pi over 3, and then I just did an extra 2 pi. Put that in your calculator if you need to. You would just enter 1/3 plus 2 is 7/3. So I have 2 semi-solutions right here. They're not really the finished answers, but I'm on my way there. Yes? No, I don't care. That's your scratch work. Some people are not going to write it all because they can do it in their head, but some people are going to write it, and some people are going to be in the calculator, and they won't be writing it either. So this is irrelevant to me. I'll be happy if you get these 2 things here. Get another one over here. So if you're going 2/3 and you're adding, an additional 2 pi to land there again, that would be 2/3. 2/3 plus 2. Remember, the 2 is 6/3. So 6/3 and 2/3. Another name for this, 8/3. So this would be the 3rd and the 4th angles that I got. Okay, I'm going to list them right here just to get them out of the mess. That was one of them. Now, these are not the final solutions because I didn't do the thing with the 2 theta that I'm supposed to do yet. And then the ones that were in quadrant 2 were 2 pi over 3. Now let me stop for a minute and see if you have any questions thus far. Okay, all I did at this point, since I was allowed to do extra spinning, is I spun right here, got the first answer. But I'm allowed to go past 2 pi. They said I could go to 4 pi, so I went like this, past 2 pi, made myself land there again, and gave it a brand new name, which is where I originally was, plus an additional 2 pi revolution. So that plus that is 7/3. I did the same thing over here. I landed on it the original time, spun around an extra 2 pi, and gave it the name of 8/3. And now we're going to fix it up so that we're using the 2 theta. Okay, any questions about that? All right, so these answers that you're seeing right here, they would be the answers if what was inside the parenthesis. These would be the answers if what was in the parenthesis was a regular theta. But it's not a regular theta. I want that I want them to be equal to 2 theta. So the way these problems finish when they have a 2 theta is you take your answer and you set it equal to the 2 theta, and that alters what you have right now. That's why these are not the final answers. So first of all, this problem had me doing general solutions. If there had been a theta in the parentheses, the solutions would look like this. It would be, just like in number 12, pi over 3 plus 2 pi k. That's what that one would look like. Okay, let's list all the answers in their general form. I'm sorry these have so many steps, but I didn't invent the problem. The next solution would be 7 pi over 3 plus 2 pi. This is if it would have been a regular theta. We're going to incorporate the 2 theta as soon as I get you to list all these. Yeah. Okay, what was that third answer? Let's see, that third answer was 2 pi over 3. So 2 pi over 3 plus 2 pi k. And that fourth answer would have been 8 pi over 3 plus 2 pi k. So all these problems that have the 2 theta, or it could be a 3 theta or a 4 theta. You would follow the same steps, only you would use the 2, 3 theta, whatever they give you at the end. So here I go, using what was actually in here, which was a 2 theta. I want this quantity to be equal to those. So here I come and do the arithmetic. Okay, I'm going to go 2 theta, using it with the first solution here, is equal to pi over 3 plus 2 pi k. I'm about to give my first real answer. Divide by 2. Divide this entire side by 2. And I guess I'm going to write everything for you. I want you to be able to follow this. Okay, keep working. We're going to take the pi over 3. Here it just cancels, leaving you with theta. Okay, so pi over 3 divided by 2 is the same thing as multiplying by 1/2. Okay, I hope I didn't lose anybody there. When you divide by 2, I'm going to say this every time I divide. When you take a fraction and you do division, this is called the divisor. It is the same thing as multiplying by the reciprocal of the divisor. The reciprocal of 2 over 1 is 1 over 2. You will always change your division into multiplication because you're going to be doing a lot of division with fractions, and that is how it's defined. Okay, I was dividing by 2. Division gets written like this. You're multiplying by the reciprocal of that number. Just flip it over and turn it into multiplication. Here, that's easy to see. 2 pi divided by 2, those would just cancel, leaving you with 1 pi k. Okay, continue fixing up. I'm just going slow for the people that don't get multiplying by reciprocal. But your first final answer, pi over 6 plus 1 pi k. Let's do this same thing to the rest of the answers. I know it is completely, you might need some time to do this problem. There's only one of them in there. Okay, here's the second one. Watch me again if you didn't get what I did when I did the first one. So the second one was 7 pi over 3 plus 2 pi k. And you want this to be equal to 2 theta. I don't care where you put the 2 theta. Put it on one side or the other. You must get the theta by itself. Therefore, you're going to have to divide by 2, divide this entire side by 2. Okay, this cancels, leaving you with theta. Let's look at the mechanics over here. The only one you need to think about pretty much is this guy right there. 7 pi over 3 divided by 2 is the same thing as multiplying by, not 2, the reciprocal. And then 2 pi divided by 2, you're going to put a k on the back. 2 pi divided by 2, these 2's cancel, leaving you with 1 pi k. Continue. 7 pi over 6 plus 1 pi k. There you go. Your second answer. Your second true answer. Everything else was just leading up to that. Okay, I divided by 2 on that side. I divided that whole side by 2 because you know you got to do the same thing to both sides of your equation. It turned this into a 6. It turned that into a 1 pi. Okay, I'm going to do this third one. I'll let you finish the fourth one. Do it one more time. I'm really doing it for the people with the arithmetic issues. Okay, so the third one was what? 2 pi over 3? 2 pi over 3 is what it looked like in its semi-finished form. But I'm dragging the 2 theta in there, and then I'm solving for theta. I want to give the answer in forms of theta. So divided by 2, divided by 2. This is the part you got to think about. You're going 2 pi over 3 divided by 2. Division by 2 is the same thing as multiplying by not 2 over 1, 1 over 2. Reciprocal. And then this divided by this, cancel, cancel. 1 pi k. Here, this is a clean cancel right there, and you get pi over 3. I mean, you could go 2 pi or 2 pi over 6, but it's going to reduce to that. So this was the third answer, and so on. Okay, I'm very bored with that routine, so let's move on. Okay, do you want to ask any questions? Anything? Okay. Let's go on to number. Now, are you guys okay with finding the 6 solutions? You take the equations that I give, and for k, you plug in 0, then you plug in 1, then you plug in 2, and then you can use the other equation. You can use any of the equations there to get the 6 answers you need. But I think they want the 6 smallest ones, so you're going to have to mess around with that. But I could already tell you, of the answers that I got, I mean, I could just tell you in general. I don't know if you could figure this out probably yourself. This was the first one I got, right? Wasn't that the smallest of the answers I got because of what's up here? Because in the other one, wasn't there a bigger thing up there? So you could get 3 answers off of this guy right here. Let the k be 0, then let it be 1, then let it be 2. You can get your calculator to assist you. And then the other one, what was the next one that we got? I think the one that I used was pi over 3. Because pi over 3 is, let me just get you to think of this. That was the third answer. What was my second answer? Okay, look at these next 2 answers. I'm just trying to save you work on when you go to find the 6 smallest answers. Somebody put in your calculator 7 divided by 6. Tell me what you get. It's 1 point something? 1.6? So this one's got a 1.6 pi in the front, and this one's got a 1 divided by 3.3. This one's got 0.3. Do you see that this is smaller than that? So when you go to get your, definitely the smallest one was the one with the 1/6 in front of it, which was that first one. Get 3 answers off of that. In other words, bottom line, what I'm trying to say to you is use the equations that have the smallest number up front, because they all had a 1 pi k. You can't use that to make the decision. So this is smaller than this. Use this to get answers 4, 5, and 6, where they were asking you to get the 6 smallest answers. All right. That problem exhausted me. Okay, so let's see. What else? We're going to go to number, how many more problems are there here? Go to, okay, calculator problems. You know how you get your calculator to do what you've been doing on paper? But again, let's be clear here. Everybody, on the test that I give you next, I don't want you touching your calculator unless it says round off or flat out says use your calculator, okay? Okay, everybody in your calculator, just real quick, if you do want to get an answer, just sine of theta. This is number 14. Do you remember how in the inverse section I taught you how to rewrite the equation to get rid of the inverse symbol? And all we did was switch these two? That's what you do if you want it to reappear. And you do want it to reappear, because the only way you can get your calculator to find an angle, the theta, is through an inverse. Inverses are about finding angles. So I want that inverse symbol to reappear. And all you do to get that to happen is switch these two. So now this becomes inverse, which is the thing that your calculator needs to see in order for it to know you want it to find an angle, and I do. If you're, the good thing about this is if you are in the undefined area, your calculator is going to tell you there is no such solution. So go ahead, put that in. You will be able to find one with this particular number, because that number has to be between 0 and 1. That was in section 7.2. If you want it to come out in degrees, yeah, maybe you should put that in your notes. When you're doing inverses, the kind of answer you want is the mode that you have to be in. So if you prefer, now what did it say? Did it say round to the certain decimal place? Then that means they want you in radians, right? Because if there aren't the only kind of answers that are decimals that you can round off to radians, radians means decimal form. So make your mode in radians. Just because of the way the directions are. But if you had a choice and you were trying to figure out what the angle was. Okay, what did you get for that? It was like 0.55? Yeah. Okay, there's more than one answer here. Let's see if I can get you to understand this. First of all, put this in your notes. The calculator only gives the reference angle. And what did you say, 0.55? That's all you got from the calculator. Wasn't there all this reasoning that I went by? Let's think about the steps. Let's mirror the steps that we did when we were doing it by hand. When we were doing all these problems by hand, didn't we, number one, figure out the reference angle? Then we tried to think of, once we found the reference angle, where should I do the drawing? And I think we did the drawing first, but there was a drawing involved, right? And when I did the drawings, did I not, right before that, think to myself, hey, what quad am I allowed to be in to do my drawing? That always flashed through my head. So, being that the sign started off positive and was still positive when you pressed it in, what quad should you be in? What quads should you be in? 1 and 2. I want you to put your rotating arm in 1 or 2. Who cares if you close up the triangle? It's all about the reference angle. Okay, we're going to be in quads where the sign is positive, and we are going to go wedge. You said I could be in quad 1 or 2. Make a full triangle if you want to. This is where the reference angle goes. And no matter what quad you're in, the reference angle is the same. It's always positive. Okay, that doesn't mean that you have the full answers. You don't have the final answers just because you do the reference angle. This section's been about pounding it in your head that reference angle and real angle are not the same unless you're in quadrant 1. So, one of my real answers, 0.55, but the answer that's here, think about what you did. We were on our way, what, to 1 pi? Now, didn't I do all this nonsense about calling 1 pi a fraction? But I shouldn't do that this time, right? Because I'm going to subtract, but aren't I doing everything in decimals this time? So why not call pi by its decimal name, 3.14? But you're not going to call it that. You're going to use a pi symbol. So we're going to leave this as is. So again, here's the reasoning. You were on your way to pi. You stopped right there. You want to know how far did you make it as you were twirling to this location right here. So remember I was telling you that when you're on your way to a landmark, which is 1 pi, but you stop right before you get there, it's going to be subtraction. So it'll be landmark. Now you're using fractions, but we're going to leave it as pi. The landmark minus the itty-bitty reference angle. And that's your other answer. The landmark. So this is my first answer. My second answer is 1 pi minus the little reference angle. I don't know what you get for that, but 2.59? Okay, 2.59. Now wait a minute. Did you use 3.14 or did you use the pi symbol? Okay, good, because my math lab marks it wrong if you try to approximate pi, because it's not exact enough. Okay, good. Everybody got it? All right, let's move on. Let's go to 16. So you see we're getting behind here, but I have to do it because these sections are not easy. Okay, so has this section been bad? Yeah? It's about to get worse. We're going to second degree now. All right, you know that whole sheet that I gave you? Instead of theorems, how I typed out all your algebra stuff? Okay, well, right now I'm just going to say it verbally. So if you don't want to write down every little thing I'm saying, I know I wouldn't if I was you. You got it written there on the sheet. Okay, let me demonstrate some of the most common factoring methods or common ways of dealing with second degree. All right, so let's see. Blah, 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 blah. You're already crying. I don't want to make anyone cry. Let's do... Oh, wait, I can't skip over 15. What am I doing? Let's do 15 first. I would like to skip over it, but which is obviously why I wrote 16, because I was like jumping ahead. Okay, let's go back to this one. I don't want to leave you hanging. Okay, so it says to do it by calculator again, right? You're going to want to use your calculator. You go over to your calculator and there's no key. So this would be a problem where you got to be creative and know how to write it so that you can use either sine, cosine, or tangent. What do you think this is related to? Who's reciprocal to this one? Cosine. So when you go to rewrite it, you're going to rewrite it in terms of cosine, inverse cosine, because that's the only way you can get an angle. But when you go to put the angle, because you know how you're going to put the angle here and the theta over here? So theta is going to go over here. Instead of writing 4.44, negative 4.44, you're going to use the reciprocal, because cosine and secant are reciprocals. Now I could do this problem for you for that, and it takes 6 steps. That's the way my math lab does it. But I could tell you it's all going to melt down to this, that you just rewrite it in terms of a function that this is reciprocal to. So be thinking reciprocals. I know you probably were going to go like this. You were going to go inverse secant. You were going to flip the number over here, and you were going to put the theta here. But, yeah, nice, but there's no key for secant. So then you just start thinking, who's reciprocal to that, and use that instead. And then also when you write this here, use the reciprocal. So 1 over negative 4.4. Put that in the calculator. That allows you to use a key that's available. So probably what I would do if I was doing this, it's up to you how you want to enter it, but I would just I would figure out probably this first, but you could put it in just like that. 1 divided by negative 4.4. I would let my calculator figure that out, and then I would do inverse cosine. But you can plug it all in at once if you want. So second inverse, paste that whole answer in there by going second answer. Close it up. Did you get that? Yeah. And what are we rounding to? All right, so anyway, get rid of this. All right, so I was telling you that the calculator only gives you the reference angle. So write that on your paper. Now, wait a minute. Secant is, hold on, we got to figure this out now. Secant, we're relating it to cosine, right? So wherever cosine is positive, secant's positive. So secant is literally made out of nothing more than cosine. So where is the cosine positive? In quad 1, because everything's, and 4. So we're going to do our pictures in quad 1 and quad 4. That completely matters. Okay, we know what the reference angle is because the calculator gave it to me. Then I want to ask myself where, oh, wait, I did it wrong. Where is the cosine? Don't I have a negative there? Where is the cosine negative? I should have been looking at that. So where is the cosine negative? You just said it was positive in 1 and 4, so isn't it negative in 2 and 3? Let's make our picture in 2 and 3. We want to know where the cosine is negative because of that negative that you see right there. That would be here and here. And I would draw the whole triangle, but it literally doesn't matter. Just what matters is the reference angle. Whenever you're putting the reference angle, put it in both places, and then let's figure out where that twirling arm is, which would be the hypotenuse. So we're going to put a 1.80 here. Don't forget, this landmark is called pi, and there would be a reference angle of 1.80 here. Okay, what do you do to get the answer in quad 2? Do you add or subtract? Subtract, because you were on your way, never quite made it there, so you are something less than pi. This is how much less? Go put that in your calculator. So second function pi minus 1.8. So 1.34. Did it say tenths or hundredths? Tenths. Okay, so 1.3. Okay, so 1.34. Okay, then the next answer, how about the one in quad 3? So you add for that one because you're going to pi and then don't you go more? So more would be indicated by the plus sign. Okay, so the second answer, the one that's in quad 3, is equal to 1 pi plus 1.80. Let me know if you get what the answer is. There's what you can write if you want to copy the work. I subtracted when I was almost to pi. I added when I had gone slightly past pi. What did you get for the second answer? 4 point what? Thank you. So those are those two. So second degree, you know, one thing you could do is you could take the trig word out. Trig word, the take the trig words out of the equation, and you would see that you would recognize what you're looking at. And then you could throw them back in. After a while, you won't have to do that. You might not have to do it at the beginning. So I want to move to yeah, now they're throwing some tricks at you here, so bear with me. Okay, so I got one that says sine squared plus cosine squared, and it's equal to 1 plus sine of theta. Okay, you might as well start getting creative because you got to be super creative in the next section. You got to know when to substitute away things that are making it more difficult. What is one of the, well, first of all, here's one thing. You know that when you're solving second degree, that if you have second degree terms as well as a linear term, that you have to bring everything to one side to factor? That's for all the factoring methods. You got to bring everything to one side. You're not going to get away with square root. That's only when you have square term and a constant, nothing more. No first degree term, and we already did a couple like that. So in this case, I am going to bring everything over to one side, but when you guys are factoring, don't you pretty much, like when you guys are factoring, you have like x squared plus 5x plus a number, but don't you have the same letter the whole way through? So do you see what the issue is with this problem that I kind of want to get rid of before I even start doing this problem? What's the issue with it? Don't know? It's two different trig words. Just like when you're factoring an equation, it's got all x's in it, it doesn't have x's and y's. You wouldn't be able to factor it if you were trying to do the kind of factoring that we're doing right now. This is called quadratic form. So one thing that I don't like is that it has two different trig words, and I'm going to get rid of that. Do you see that it's mostly sine? You got sines here and sines here. So the majority of the terms have the word sine. I'm going to go all sine. I'm going to substitute for this. Okay, now I know somewhere, probably in two different sections, I'd given you a sheet. I bet you it's the one for 7.4, and it's got like all the identities and the theorems and everything. And there was one identity that I believe I started giving to you back in chapter 6 that went sine squared plus cosine squared is equal to 1. It's one of the basic Pythagorean identities. Why don't you write that over here? You're going to be using it endlessly in the next section. Sine squared plus cosine squared is equal to 1. I'm going to make this guy go away because I'm going to use this to help me make that go away. If you want this term to go away, you have to isolate this word in the equation that you're going to use to do substitution. I'm planning on doing substitution here. Isolate this word so that you can then go and substitute. If I want to get this by itself, I just bring this to the other side, that's all, and it becomes negative sine squared. So isolating the word cosine squared, it would be 1 minus sine squared. Okay, so whenever you got to learn this. When you go into the next section, you're going to see yourself like always substituting. It'll be substitute, then algebra, substitute, then algebra. Super algebraic. You're going to get away from all the spinning and the triangles and the reference angles and go to something completely different. And it'll have to do with your algebra skills, your factoring skills, your solving skills, and your ability to substitute. So here's one of the most basic things we do in the next section. We take a Pythagorean identity. This is one of the three. And whatever you're substituting for, in order to do the substitution, you need to get that word over here. You need to get that word by itself, isolate it. So all I did is bing. Now, a lot of students will do this in their head. At the beginning, you'll probably be showing it to yourself on paper. Now, take this expression, which is equivalent to cosine, and swap one for the other. Okay, I'm going to come right in here, and where it says cosine squared, I'm going to put its equivalent, 1 minus sine squared theta. I got a 1 and a sine theta over here, and now I have an equation. I'm copying all the rest of the terms. There was a negative sine squared in the front. There was all this on the right. But anyway, now at least I have a problem that is nothing but the trig word sine. which will allow me to factor it. While you have sine and cosine in the problem, good luck. You're never going to factor it. Okay, so come now, bring everything to one side. Why? Because it's second degree. You also cannot factor unless you zero out the equation. Now, I'm not going to write this on paper. I have already painstakingly typed out every bit of those comments on that sheet that you have. So I'm going to say it verbally. When you factor, you need to zero it out. So I'm going to bring everything over here and zero out the right side. So it's negative sine squared plus 1 minus sine squared equal minus 1, because I'm bringing this 1 over here, so it becomes negative 1. The sign becomes negative sine. You know, things switch sign as they move from one side to the other. So I'm going to get my 0 on the right side. Everything's on the left now. Okay, start canceling things that cancel. Like we have, let's see, the go away. Go away. That makes it a little nicer. Both sides. So we'll go negative 1 plus negative 1, negative 2 of that particular term. Cleaning it up. Okay, first factoring method that I am going to demonstrate in order to break down second degree and make them both first degree is called the Gcf method, taking out the greatest common factor. Do you see that both of these terms have at least one sine term, sine to the first degree? So I'm going to yank that out as the common factor. This is called the Gcf factoring method. So I'm going to go, and you can take out the negative as well. I'm going to take out negative sine. That's common to both of these, and they both have at least one sine. Whenever you're doing this Gcf method where you're pulling out a common factor, that is the only factoring method that only has one parenthesis. The rest of them have two. Okay, so then let's see. Let's get back the original terms, this and this, by using the Gcf that you pulled out as a multiplier. So this times what is this? Sine theta. This times what is that? Positive 1. Check it again. Sine times sine, sine squared, negative, and let's see. Oh, what else do I need? I need a 2 somewhere. I'll put the 2 right there. So now, negative 1 times 2, there's my negative 2. Sine times sine, sine squared. And then negative sine times 1, negative sine. There, I got it all factored. That's called the Gcf method. There's 5 factoring methods from Algebra 1 and Algebra 2, or whenever you last took it, MAC1114, whatever. 1033, they do all these. It's just that they do it with x's instead of trig words. Okay, once you have broken down the second degree and you no longer have second degree, which is what factoring is about, it's to get rid of the second degree, you're going to use what's called the zero factor property. When two things multiplied together give you a 0, that means either this one must have been 0 or that one or both of them. That's what enables you to make these little baby equations. And then you are right into where we started at the beginning of this section. Finding the solutions that go with this and this. Twirling around if you have to. Okay, the answer for this, there's only one of them. Whenever you're doing sine or cosine, just sine or cosine, and you have zeros or ones, that's when you're only going to have one answer, no triangle. One answer, no triangle. Oh, wait, you could have more than one answer when it's 0. Just no triangle. You're not going to have a triangle. Okay, not, and then that one's going to have a triangle. Okay, so if you're getting rid of the negative 1, it's sine of theta equal to 0. Think about this circle. Here you go, right here. You got 1, 0 here. You got 0, 1 here. You got negative 1, 0 here. If you have to put these numbers on every single location to get your head straight, then do that. What does the front number represent in each of those pairs? Cosine. Okay, so we're looking for sine, right? We want to know where the sine is 0. What are those locations? There's more than one of them. Okay, right there and also right there. This is called 0, the 0 location. This is called pi. I just got two answers. 0 and pi are my first two solutions. I'm going to put the solutions down here. Let's get the answers for the other one. Okay, when this is first degree, you got to isolate the trig word. This is what we've been doing in all the problems in this worksheet. Leave the 2 there. Swing that 1 over to the other side. Divide by 2. Sign is 1/2. There's a negative. Okay, I would like to know where to draw, so I want to consider the fact that sign should be negative. That happens here and here. If you want to complete the triangles, do so. You can split these numbers up if you want. Sine is defined as y over r. And my r is there. Okay, again, let's think about this together. If there's a 2 and a 1 right here, what does this guy have to be, short leg or long leg? Okay, it has to be the short leg because those formulas go. That hypotenuse is twice as big as the short leg. Okay, so for those, as soon as you know this is the short leg, you have to recall at that point, short leg is always across from the 30-degree angle, which is also called pi over 6. All right, knowing that that's pi over 6, let's go in for those answers. What is this guy called right here? Let me put the crutch of the landmarks. This is called 6 over 6, 1 pi. This is 12 over 6. So where is this guy at? How many 6s are you at in that quadrant? 7 6s, that's my third answer. And how about this guy in quad 4? See how good you're getting? Those are the 4 answers. Okay, I have to factor this next one for you. I'm sorry, I don't have a minute to waste because I am already one whole class behind now because I took so long, but I can't see you having any success at all if I didn't do that. Let's go to this one quickly, 17. Those problems that you've been working on together, you're going to keep them again because we're going to add on to them next time I see you. Okay, this one was already zeroed out. Okay, what this is like is 2x squared minus 9x plus 7. I bet you guys are